Okay, so we will start with this paper, October, November 2022. Okay, so this is paper 2. So question number 1, okay, if you look at question number 1, okay, atoms with nuclei containing odd number of proton tend to have fewer isotopes than those with an even number of proton. So gallium now have 2 stable proton, so with the 69 and 71, so this one is going to be the mass number. Yeah, so if they ask you to define isotope is compounds. Isotope is species that has the same proton number but different number of neutrons. Okay, so complete the table 1.1 to show the number of proton, neutron and electron in the 2 stable isotopes of gallium. So if you look at gallium 69, okay, so number of proton, okay, so this number of proton, okay, for gallium what we can do is we can refer to our periodic table. Okay, so gallium, let's look for gallium Ga.
13.
Where?
13.
Okay, 31, yeah. So 31, so we have this over here, 31. Okay, so the number of proton is 31. So this one, both of them, 31, 31. So number of proton is 31, both of them. And number of neutron is going to be the difference between proton and the mass number. Okay, so 69 minus 31 is going to be 38. Number of electron will be the same as number of protons, so 31. Okay, so similar over here, number of electron for gallium 71 is also 31. Okay, number of neutrons is the one that is going to be different. You find the difference over here, that's going to be 40. Okay, those are going to be the answer. Now define relative atomic mass. Okay, so relative atomic mass is the mass, okay, of one atom. Okay, the mass of one atom in comparison to the mass of, or in comparison to 1/12 mass of one atom of carbon 12. Okay, if I put it again, so it's the mass of one atom, okay, in comparison to the 1/12 of the mass of one atom of carbon 12. Okay, so if I want to write down the formula also, RAM, relative atomic mass, is going to be the mass, okay, mass of, I think no need to write. Okay, just straight away I think just leave it like this, or we can just check the marking key. Okay, marking key, they say that paper 2. Okay, so the marking key is the average or the mean mass, okay, of the isotope or average mass of the atom of the element compared to the mass of unified atomic mass unit. So this one is slightly different definition. Okay, so the definition for relative atomic mass is going to be the mean, okay, according to the marking key, is the mean mass of the isotope. Okay, this one again, I feel this one is much more better. Okay, because why? Okay, the mean mass of the isotope, they didn't ask relative isotopic mass. Yeah, so the answer given here is more like average mean mass of isotope, average mass of element. Actually supposed to be average. okay, we take the average mass of the element, average mass of element, okay, because elements can have isotope, okay, compared to the unified atomic mass unit, okay, unified atomic mass unit. So the unified atomic mass unit is the mass 1/12 of the mass of one atom of carbon 12, okay. So which is 1/12 of one atom of carbon 12. Now, so let's move on further. So the relative atomic mass, okay, of gallium is going to be 69.723. The relative mass of gallium, yeah, so they actually give you all this, the mass. Okay, use the information to calculate the percentage of abundance of this, okay, in elemental gallium. Show your working. So let's say, okay, if you want to do this, okay, so we take the percentage of abundance of gallium as X, okay. So if you have gallium is going to be X, okay, gallium 71 should be what? 100 minus X. Do you agree with me? Yeah. So gallium is X, so gallium 71 should be 100 minus X. Okay, so assume the element contains only these two. That's why we actually put the 100 minus X. Okay, so now we are going to actually calculate. Okay, so in order to calculate the relative atomic mass, okay, 69.723, you calculate from, okay, the percentage. So the percentage is going to be mass X over 100, okay, times gallium 69. Gallium 69 is this, okay, so 68.926, and then plus, okay, this one is going to be 100 minus X divide by 100 times, okay, with the this one for 71, 70.925. Okay, so what we need to do is to find the X. Okay, so help me with this. Okay, 69.723 equals to 68.926X plus 100 is 7092.5 minus 70.925X divide by 100. So this one is 6972.3 equals to 68.926X minus 70.925X plus 7092.5 divided by 100. Okay, so you just minus for me 68.926 minus 70.925. Okay, negative 1.999. So plus 70. Okay, this is X 7092.5. Okay, just now I already times by 100, so no need. So 6972.3. Bring this one over here, it will become 1.999x 7092.5 minus 6972.3. Okay, 7092.5 minus 6972.3. 6972.3. 120.2 1999x, X equals to 120.2 divided by 1.999. 60.13. Okay, we want 4 significant figures, so 60.13%. So that's actually gallium, which is we found the X, so that is X value that they wanted. Yeah. Okay. Now next, okay, potassium also have 2 stable isotopes. Okay, both isotopes have the same chemical property. Explain why both isotopes of potassium have the same chemical property. So isotopes have same chemical property because they have the same number of electrons. Okay, because they have the same number of electrons, therefore, okay, chemical property is the same. So let's actually keep checking the answer key as well. Okay, so they have the same electron arrangement. Okay, so that is what they gave, or same electronic configuration. Okay, rather than saying the same number of electrons, okay, we will actually give the answer as same electron, because they have the same electronic configuration. Now state the full electronic configuration of atom of potassium. Okay, potassium is 19. Okay, so if you want to write the full electronic configuration, so it's 1s2, 2s2, 2p6. Okay, then it's already 10 here. So 2p6, 3s2, 3p6, that's already 18. After that, after 3p6, do we go for 3D?
No.
Okay, we will skip 3D, we will follow 4s1 first, then only we fill up 3D. Okay, so the potassium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Okay, the first, second, and third ionization of energies of potassium, okay, is 418, 3070, and 4600. We can see, okay, there is going to be a big jump, okay, from the first ionization energy to second ionization energy. Okay, use this information, okay, why potassium is in group 1. So you can see, to remove the second ionization energy is really high compared to the first ionization energy. It means that, okay, to remove the second electron, okay, it's going to be, you need to give a lot of energy. Okay, you need to give a lot of energy, or it's difficult to remove the second electron. So it means that the first electron is already at the outermost shell. Okay, so second electron must be closer to the nucleus, must be in the inner shell. Okay, so use this information to explain why it is in group 1. Okay, because, okay, the second, okay, ionization energy is really high compared to first ionization energy. It means that the second electron is in the shell that is closer to the nucleus. That means one electron earlier must be in the outermost shell. Okay, so that is going to be group 1. Okay, so here if you check again the marking key, so there is a big increase in ionization energy between first and second. Okay, so I say really high. I think it's better to actually follow the marking key, because they say there is a big difference between first ionization energy and second ionization energy. Okay, I think this is much more better way to put it. And then they say that, okay, the second electron is removed from the inner shell. Okay, so I use the term shell that is closer to the nucleus, that is meaning inner shell, still okay. And then so it is removed from the shell closer to the nucleus, that is actually what we have written. And the second electron has stronger nuclear attraction. Okay, so we didn't write it down, so you just need to write down the electrons in the inner shell. Okay, the electron in the inner shell experience greater attraction. Greater attraction from the nucleus. Okay, now so next, question number 2. Now magnesium shows reactions typical of group 2 metal. Now draw a label diagram to show the bonding in magnesium metal. So magnesium is metal, so we need to draw, okay, the cations. Okay, that's very important. So you just draw like this. Okay, so we can actually copy this, copy, paste. Okay. Okay, the idea is to show that, okay, this is going to be cations. Okay, I think I'll just simply draw. Okay, so what I'm going to do is just going to put positive there, positive, and then put the electron. So the electron negative, just put outside, okay, in any gaps over there. So they say a label diagram, so a lot of students miss out that, okay, they forgot to label. So this one is going to be magnesium ion. Okay, so magnesium ion, normally they form 2+, but it's okay to show 1+, it's okay. So this one is delocalized electrons. Okay, so the bonding between the positive and the negative, the C of the delocalized electron, okay, is going to be known as metallic bonding. Okay, so if you look at the marking key, okay, let's see what is being expected from you. So you can see they have written the ion, delocalized electron, and they actually leave a lot of space to show the delocalized electron. It's okay, okay, if it is right like this, at least we can see, okay, there's a lot of electrons surrounding, yeah, the metal cation. Now, next question. So the figure 2.1 shows some of the reaction of magnesium and its compound. So magnesium, okay, when you add with ACl, they give you magnesium chloride. Then after that, when you react with calcium hydroxide, it gives you magnesium hydroxide. Now, we also have reaction of, okay, magnesium carbonate reacting with ACl, okay. Do remember acid, earlier acid and metal, okay, they will give you salt and hydrogen gas also, okay. So magnesium carbonate with ACl, they will give you salt plus carbon dioxide and water, okay. So they are for reaction 2, that is carbon dioxide and water. Now reaction 4, okay, is heat. So what is this? Magnesium carbonate to change it to magnesium oxide. What is that?
Just heat it.
Just heat, but this reaction is known as thermal decomposition. Okay, thermal decomposition. So what thermal decomposition for magnesium carbonate? Magnesium carbonate, they will decompose to give you magnesium oxide plus carbon dioxide. Okay, if you have, okay, nitrate, okay, let's say for example magnesium nitrate, okay, if you have thermal decomposition, then you will have magnesium oxide plus nitrogen dioxide, and you will have oxygen gas also. Okay, so please take note of this balancing. Yeah, you can do yourself. Okay, but if nitrate, then you have the magnesium oxide or the oxide, nitrogen dioxide and oxygen gas, not nitrogen gas, yeah, nitrogen dioxide. So here identify the other products of reaction 1 and 2. So we already have reaction 1, magnesium chloride, plus what? Plus hydrogen gas. Okay, so hydrogen gas. Reaction 2, okay, so magnesium carbonate react with ACl to give you salt, and then you have carbon dioxide and water. Do remember, must give both. Okay, so carbon dioxide and water, carbon dioxide gas and water. Reaction 3 is used to form precipitate magnesium hydroxide from magnesium chloride. Okay, so reaction 3, from magnesium chloride you get magnesium hydroxide precipitate. Now, state why calcium hydroxide will not form precipitate, okay, of barium, okay, hydroxide, okay, from barium chloride. Okay, so here, okay, reaction 3, okay, magnesium chloride, okay, is reacting with calcium hydroxide, okay, to form magnesium hydroxide. So state why calcium hydroxide, okay, will not form a precipitate of barium hydroxide from barium chloride. Okay, calcium hydroxide reacting with barium chloride. Why cannot form barium hydroxide? Okay, why cannot form this precipitate? So this one, okay, most likely, okay, if you look at this reaction, okay, so magnesium chloride, okay, they react, okay, with calcium hydroxide, okay, to give you magnesium hydroxide. Okay, it's a precipitate. Calcium hydroxide reacting with barium chloride to give you barium hydroxide. So basically, I think if it let's look at the barium hydroxide. Okay, so if you look at hydroxides, okay, so when you go down, okay, we know the barium sulfate. If sulfate, barium sulfate, precipitate will be formed. Okay, but if you go down group 2, okay, barium hydroxide, okay, barium hydroxide is not is going to be soluble. Okay, so hydroxide of group 2 going down the group, okay, they are soluble. So in this case, okay, you will get a soluble salt of barium hydroxide rather than a precipitate. Okay, so state why calcium hydroxide will not form a precipitate of barium hydroxide from barium chloride. Okay, so because, okay, the answer is because barium hydroxide is soluble and will not form a precipitate. Okay, let's see what is the answer. Okay, it should be soluble and will not form precipitate. Yeah, you can see. So barium hydroxide is soluble in aqueous solution. Solubility of hydroxide increases down the group. Yeah, so you just need to apply that. Why? You no need to worry because that's A2 work. Okay. Now state the type of reaction that occurs in reaction 4. So reaction 4 we already know. Okay, what is that? Okay, thermal decomposition. Now 1 cm cube of magnesium chloride is placed in a test tube. A few drops of silver nitrate are added, followed by dilute ammonia. So please remember, silver nitrate is contributing silver ions. And then you have magnesium chloride, you have Cl minus ion. So these two, when you join in, okay, you are going to get silver chloride. Okay, so Cl minus plus Ag plus, you will get silver chloride. Do remember, AgCl is white precipitate. AgBr is going to be cream precipitate. AgI is yellow precipitate. Now, we can further confirm this reaction by adding dilute ammonia or by adding concentrated ammonia. So if you add dilute ammonia, silver chloride, the white precipitate dissolve. Okay, so if it is dilute, dissolve, concentrated, of course it will dissolve. Now silver bromide, okay, on the other hand, dilute ammonia, they don't dissolve. Okay, the cream precipitate will not dissolve. But if you are using concentrated ammonia, it will dissolve. Now the stubborn precipitate is silver iodide. Silver iodide is yellow precipitate. If you use dilute ammonia, no, okay, it will not dissolve. If you use concentrated ammonia also, no luck, okay, it will not dissolve. Okay, so state in full what is observed in this reaction. So we are talking about silver chloride. Silver chloride is a white precipitate. Okay, so a white precipitate is formed. Then the white precipitate dissolves in excess of dilute ammonia. Now, when 1 cm cube of magnesium chloride is added to Br2 in a test tube, the solution remains orange. So it means that MgCl2 plus Br2. Okay, so we are trying to actually see whether you can displace, okay, MgCl. So Br, if you look at Cl, Br, Cbi, yeah, Cl is more, okay, it's more reactive at higher position compared to Br. So it means that Br cannot displace, okay, these two couple. If you want to remember couple, boy and girl, they Br2 is not able to displace that, okay. So what happens, they will remain as Br2, they will remain as MgCl2. It means there is no reaction, okay. Why? Okay, then in order to say why, okay, because Cl2 they were in Cl minus form, so -1. If it displace, then they will become Cl2, which is going to be 0. So the oxidation number that is going to happen is going to be -1 to become 0. So -1 to become 0 is oxidation reaction, okay. So you can say that, okay, Br2 is not able to oxidize Cl minus to Cl2, okay, it's not able to oxidize Cl minus to Cl2, and therefore no reaction happen. The solution remain orange. Okay, 9 marks. Settle, yeah? So number 3. So number 3, some of the chlorides of period 3 elements are shown in the list. So from this list, identify all the chlorides that have giant ionic. Now giant ionic is going to be metal and non-metal. So let's actually see. This is metal and non-metal, metal and non-metal, metal and non-metal. Okay, this is non-metal. Okay, this is non-metal. So in this case, okay, all the chlorides, so NaCl, MgCl2, okay, AlCl3. Okay, all these are giant ionic structure. All the chlorides that reacts vigorously in water to form strongly acidic solution. Acidic, yeah. Acidic means it must be a metal oxide. Okay, metal oxide is basic oxide, so it must be a non-metal oxide. Okay, they will form a strongly acidic solution. So the non-metal oxides, okay, we have SiCl2, Cl4 and PCl5. Now we need to be careful, okay, whether SiCl2 will they react with water. Okay, so I'll leave it to you now. SiCl2, do they react in water, Kevin? Should be. Okay, SiCl2, okay, we check, yeah, but definitely the answer is PCl5. Okay, but SCl2, okay, do remember they are non-metal, okay, chlorides. Okay, so see whether they react vigorously with water. Okay, let's see the marking key. Hold on, just now they use remain orange. Okay, that one is, so Br2 is not strong enough as oxidizing agent. Okay, still okay. Okay, number 3I. Okay, so 3A2. 3A2, yeah, 3A2 is here.
Al is another person.
So Al, okay, so they are taking it as, okay, so the giant is not including aluminium. Okay, so sodium and magnesium. Okay, so maybe aluminium is special case. So all the chlorides that have giant ionic structure in the solid state, maybe in the solid state, yeah. Now, so NaCl and MgCl2, all the chlorides, okay, that react vigorously to form acidic solution. So this one is going to be Al, Cl3, PCl5, and SiCl4. Okay, so they will actually give you HCl. Okay, so ACl3, PCl5, SiCl4. Okay, all of them, they react vigorously with water to form strong acidic solution. The chloride that dissolve in water to form a neutral solution. NaCl, yeah. NaCl is the one that will actually dissolve in water to form a neutral solution. The chloride formed from the element, okay, with the highest melting point. The chloride formed from the element with the highest melting point. The one that is most highest melting point over here, okay, should be SiCl4. Okay, so the chloride formed from the element, okay, with the highest melting point. Okay, so okay, we will actually take SiCl4. Okay, because this element has the highest melting point. Okay, so you can see it from the graph in the textbook. Okay, it's there. Now, NaCl is one product of reaction of chlorine gas and coal. Now, under coal, okay, please remember NaClO will be formed. Okay, but if they say hot concentrated sodium hydroxide, then they are going to form NaClO3. Do you remember this? Okay, if it is coal, NaClO. If it is hot, you will get NaClO3. So NaCl is one of the product of the reaction of chlorine gas and coal aqueous sodium hydroxide. So if you have Cl2 plus NaCl, you get NaOCl or NaClO plus NaClO plus what? Water, yeah. Water. Okay. Plus water. So Cl2 plus NaCl, okay, to give you NaCl2 plus H2O. NaClO, where this O coming from? The formula for this. Sodium hydroxide. They say, oh, sodium hydroxide is not sodium chloride. Sodium hydroxide. Okay, so you get NaClO plus H2O. Yeah, then only we can remove the hydrogen. Yep. So this one, they didn't ask you to balance the equation. In this case, they just asked to identify another product. The another product is going to be water. Okay, identify the other products. Water. Should be only water. Identify the other products. Why they say products? Okay, basically they react, okay, so identify the products. Okay, so the products, okay, I think it should be more clearer. So product is NaClO plus H2O. These are the products. Okay. Now PCl5 reacts with alcohol to form chloroalkanes. Do remember PCl5 is a test for alcohol. Okay. Why? Because it gives you the steam white fume. Okay. It's a test for alcohol. So to form chloroalkanes, identify this type of reaction. Okay. So ROH, okay, plus PCl5. Okay, you will have RCl plus, okay, RCl plus HCl, RCl plus HCl, then there is 3Cl some more. So POCl3. Okay, I think that's POCl3. I think that should be it. Yeah, POCl3. Okay, so in this case, okay, identify this type of reaction. Yes, it's a substitution. Okay, the OH is substituted by Cl, so substitution. Or you want to write down, okay, nucleophilic substitution also can. Okay, draw the structure of organic product formed in the reaction of an excess PCl5 with butane 1,3-diol. Okay, so this is butane, position number 1, okay, position number 3, okay, diol. Okay, so now you are reacting with PCl5. So we want organic product. So what happened? The Cl will come here, the Cl will come here. Okay, draw the structure. Okay, so excess. So I think CCl, C, another Cl will be here. Okay, so just put all the hydrogen. Okay, so let's quickly check the marking key. Okay, you can see the Cl here at position 1 and Cl at position number 3. So they say that sulfur reacts with chlorine to form different chlorides. Okay, the most common is S2Cl2, then SCl2. So we have two equations over here. From these two equations, okay, what we want to find out is going to be, they say that we need to, first of all, the first question, okay, they say SCl2 is a cherry red liquid that reacts vigorously in water to form acidic solution. So we want to deduce the bonding and the structure of SCl2. So to deduce the bonding, first they are reacting with water, okay, and they also mentioned that it's a cherry red liquid. So from here, if it is liquid, then we know that they have low boiling point or melting point. Okay, so that's an indication that this is going to be a simple molecule. So that's the first answer, simple molecule. Now the bonding, okay, we can actually deduce that the bonding is going to be covalent because they are reacting with water. They react violently with vigorously with water to form acidic solution. So it means that the bonding is covalent, okay, because it is going to be hydrolyzed. Okay, they are going to be reacting with water. Okay, so that is going to be the explanation for D1. Now for second part, okay, they are asking us to calculate the enthalpy change of formation of SCl2, and they say you may find it useful to use Hess's law to construct energy cycle, but I'm not going to use the traditional way to construct the Hess's law cycle. Okay, what I'm going to do over here is, when I see here, I see S2Cl2 and then S2Cl2 over here. What I'm going to do, I'm going to combine these two equations. I'm going to eliminate the S2Cl2. Okay, so in order to eliminate the S2Cl2, reaction 2, I need to times by 4. So when I times by 4, I will have 4, this will become 8. So here I'm going to times by 4. So when I add these two equations together, I'm going to get S8, okay, then plus, okay, 4Cl2, 8Cl2, and this, okay, 4S2Cl2 will be cancelled with this, okay, so it will be cancelled. So left with okay, so therefore there is no plus here, so it will give you 8 SCl2. Okay, so the enthalpy change over here is, okay, we add these two, so negative 58.2 plus, don't forget, it's times by 4, so 4 times negative 40.6. Now this is, we are going to get this enthalpy change, but if you look at it further, this is element, this is also element, and then you have SCl2 which is in liquid. So they say enthalpy change of formation. The definition of enthalpy change of formation is when you are forming 1 mole of the compound from its element. In this case, you are forming 8 moles. Okay, so what you need to do, this is going to be the enthalpy change, okay, for 8 moles. So you need to divide by 8. Okay, so we want for 1 mole. So when you divide by 8, you are going to get the value which is going to be negative 27.6 kilojoule per mole. Okay, so the enthalpy change of formation is going to be negative 27.6 kilojoule per mole. Now, the next question, state the effect of decrease in pressure, okay, on the position of equilibrium in reaction 2. So if you look at reaction 2, okay, so they want to say decrease in pressure. So whenever we look into decrease in pressure, the one that is going to be affected is going to be the gas only. Yeah? So the gas on over here on the left hand side, okay, there is only 1 mole. Okay, 1 mole, okay, on the left hand side. On the right hand side, there is no gas, so 0 mole over there. Okay, so now when I decrease the pressure according to Le Chatelier's principle, LCP, you need to increase the pressure. How do we increase the pressure? Okay, we increase in favoring to form more number of molecules. So you form from 0 to 1. Okay, so the position of the equilibrium will be shifted to the left or to favor more molecules. In this case, we are talking about 1. Okay, so state the effect. Okay, the effect is going to be the position. Okay, the position of the equilibrium will be shifted. Okay, of equilibrium will be shifted to the left. Okay, will be shifted to the left or to form more reactants. Okay, to form more reactants. Okay, to favor. Okay, to favor more number of molecules. Okay, so here if you look at the explanation from the marking key, equilibrium move to the left and more moles of molecules of gas on the left hand side. So in this case, this one, our answer is okay. The position will be shifted to form more reactants, okay, to favor more number of molecules. So if you want to make it clear, the position will be shifted left, okay, to form more reactants to favor more number of molecules. Okay, you can add of gas. Okay, so that's going to be the answer for this. Okay, so let's move on further. Okay, so now they say figure 3.1 shows 2 structural isomers of S2Cl2. Okay, so you have 2 structure. Okay, define the term structural isomer. Okay, so structural isomer is going to be molecules, okay, that has the same molecular formula but different structural formula. Okay, same molecular formula with different structure. Okay, so the answer, okay, is going to be or, okay, you can say same molecular formula, so that's going to be number 1 mark, but different structural formula or different structure. I think better to say structural formula. Okay, let's follow the marking key. Now, suggest a value, okay, for Cl, S, and S bond angle. So they want this bond angle. Okay, so explain your answer. Okay, So in order to find this, okay, you need to find out, okay, first, okay, the center molecule, the center atom is going to be sulfur, okay. Then you check, okay, sulfur has two bonding pair, okay, one bonding pair is here, another bonding pair is here. So you have two bonding pair. Now check whether they have lone pair or not. Sulfur is going to be group 6 or group 16. Okay, if you have group 16, okay, so 2 electrons are going to be shared, okay, so for covalent bonding, and you are going to have, okay, another 2 lone pair, okay, that will make it total 6, okay. So we have 2 lone pair also, okay. So this structure, two bonding pair and 2 lone pair, is similar to the structure of water, okay. So the bond angle, okay, is going to be this one is going to be non-linear, okay. So the bond angle will be similar to water, which is 104.5 degrees, okay. You can memorize this explanation because, okay, sulfur has 2 bonding pair of electron and 2 lone pair of electrons, which forms a non-linear structure. Okay, so the answer here, okay, they say anything from above 90 less than 108, okay, they do accept. Okay, so ours is 104.5, it's okay. Now sulfur has 2 lone pair and 2 bonding pair, okay. So there is N over there, so our answer might be only given 1 mark, okay. So they want, okay, they want 2 marks over here, so I think we still need to give more explanation to this. Okay, the explanation is the repulsion, okay, and the repulsion between, okay, the repulsion between the lone pairs. So this is to explain why you have 2 bonding pair, 2 lone pair, why it's not like counted similar as 4 bonding pair, why it's not 109.5, yeah. So you need to tell, okay, because the repulsion between the lone pairs are greater. So you need to explain that. So without that, even though our previous answer is correct, you might not get that mark, yeah. So we might end up with getting only 1 mark, okay. So we need to mention about the repulsion. Now next question, draw a dot and cross diagram to show the bonding in isomer 2. So show the outer shell electrons only. So we want to show the bonding, okay, outer shell only, okay. Sulfur, okay, so you have sulfur, so I will draw sulfur, and then I have Cl, okay, so I will draw for Cl. I have another Cl, so I'll draw for another Cl. So we have another sulfur, so we draw for sulfur. Now one thing is, okay, for sulfur we know it's a double bond, so we will actually put double bond, okay. So dot dot, okay. Each sulfur, okay, must have 6 valence electrons. So let's say the dot is going to be for the sulfur on top, yeah. So 1 2 3 4 5 6, okay. So I put it like this, and then so now for X, okay, so single bond, so X from here, X from here. So let's say I'm going to put dot for Cl, okay. So Cl 7 valence electron, group 17. So another dot, 7 valence electron. And we know that sulfur, okay, sulfur is going to be the X, so sulfur is group 16, so 6 valence electrons. So therefore now we have total 4. I need another 2 more, okay, so it will exist as lone pair of electron. So that's going to be the answer. Okay, next. Okay. Okay. All right. Next. So organic compounds can be distinguished using chemical tests. Okay, this is similar like what we did earlier in the previous paper. So here they say table 4.1 shows 4 pair of compounds. Okay, so if I look at the compounds over here, okay, I have this one as ester. Okay, I have alcohol here, and this alcohol is a secondary alcohol. And here this is ester. Okay, this is going to be a ketone, but this ketone is special because it has the CH3 group over here. Okay, CH3 group over here. So this is going to be cyclo 1 2 3 4 5 cyclopentane. Okay, cyclopentane. So basically single bonds. Okay, and then we have this one alkene. Okay, there's an alkene. And then I have alcohol, okay, with many OH groups. Okay, and I have carboxylic acid here, and I also have alcohol, but in this case, what kind of alcohol? In this case, is going to be a primary alcohol. This is a primary alcohol. But if you look over here, this one also, this part, the OH, this is also a primary alcohol. Okay, primary alcohol. This, there is C, so this part is secondary alcohol, and this is also going to be a primary alcohol. Okay, so all this, okay, will actually help us, okay, to answer our question over here. So complete table 4.1 to identify a region that could distinguish between the compounds in each pair. Give the positive result and identify which compound shows the result. Okay, and use different region for each test. Okay, we cannot repeat. Yeah. So now, okay, I have ester and I have a secondary alcohol. Okay, so how do I actually differentiate, okay, ester with secondary alcohol? Okay, we know secondary alcohol we cannot further oxidize, so maybe we can use this one, okay, to identify alcohol. We can use PCl5. Okay, PCl5 is an indication, okay, of okay, PCl5, okay, is an indication for alcohol. So if I use PCl5, okay, that's the region. The positive result is going to be steamy white fume. Okay, steamy white fume. Okay, with A2 because of alcohol. Okay, so A2 is alcohol, so steamy white fume. And then let's say now I have ketone and ester. How do I differentiate ketone and ester? Okay, so you can use, let's say for example, two methods. Okay, you can use many methods actually. Okay, you can use 2,4-DNPH. You can use Phelling. No, Phelling is for aldehyde only. Yeah, you can use 2,4-DNPH. Okay, or you can actually use the triiodomethane reaction. Okay, because there is CH3 group over there. Okay, so how to identify? So now I want to identify ketone. Okay, you can either use 2,4-DNPH. Okay, so if you use 2,4-DNPH, it's a test to identify aldehyde and ketone. So here, if I use 2,4-DNPH, then I am going to get an orange precipitate. Okay, you will get an orange precipitate. If you use, okay, they say only one, okay, but let's say you want to use triiodomethane reaction, so NaOH with I2, okay, or alkaline iodine, okay, alkaline iodine triiodomethane reaction, you will get yellow precipitate, okay, because of the B1. So both of them for B1. Okay, so choose only one, okay, when you answer. Okay, so now to differentiate C1 and C2, quite simple. There is double bond over there. First thing, please add Br2, bromine. Okay, so the orange, okay, or brown, okay, color will be decolorized. The orange color will be decolorized. Decolorized by C2, presence of carbon-carbon double bond. Now, so the next one, D1 and D2. Okay, so you have alcohol and you have carboxylic acid, you have primary alcohol, secondary alcohol. Okay, so how do you want to differentiate this? Okay, alcohol, okay, they react with sodium. Okay, carboxylic acid also will react with sodium. Okay, so the only difference over here is carboxylic acid can react with sodium hydroxide. Okay, alcohol cannot react with sodium hydroxide. Okay, so when you react, okay, maybe if you react with sodium hydroxide, okay, they are going to give you acid will react with sodium hydroxide to give you salt and water. Okay, but positive results. Okay, positive results, salts and water. Water is produced. Salt and water. Okay, is there other things that are more visible? Okay, let's see. Alcohol, primary and secondary alcohol, you are reacting with carboxylic acid. Okay, primary alcohol. I think the best is by using sodium hydroxide. Let me check also here. Okay, rather than using sodium hydroxide, that's why they don't use sodium hydroxide, because we cannot see the observation clearly because water. Yeah, you can react with sodium carbonate. Okay, sodium carbonate acid will react with sodium carbonate to give you carbon dioxide. So carbon dioxide, okay, you can actually, because alcohol do not react with sodium carbonate. Yeah, so carboxylic acid reacts, so the carbon dioxide you can test using lime water. Yeah, so here you react with sodium carbonate. So what happens? D2 will release a gas which turns lime water cloudy. Okay, so D1, okay, will not react with sodium carbonate. Okay, so you can use, okay, this, okay, okay, in the answer key, okay, for first part, okay, they say they use K2Cr2O7, okay, KMnO4. They even use sodium. Okay, but I think I use PCl5 is still acceptable. Okay, PCl5 you can still get the steamy white fume. Now, so here, okay, according to the answer, okay, they have used, okay, alcohol. Okay, so they use sodium. If they use sodium or any of these oxidizing agent, okay, if you use the oxidizing agent, okay, A2, okay, because it's a secondary alcohol. Secondary alcohol can change into ketone. Okay, so you can use oxidizing agent. Okay, the A2 will still give positive results. Okay, if you use KMnO4, purple color will become colorless. K2Cr2O7, orange will become green. If you use sodium, then you will have hydrogen. That hydrogen gas is going to be giving the pop sound with lighted wooden spoon. Okay, all this. Okay, so if you want to use that, it's okay. PCl5 is still correct. Okay, it's a region to find out presence of OH. Okay, now C1 has melting point of -94 and boiling point of 49. Okay, explain these properties by referring to the type of van der Waals forces between the molecules. Type of van der Waals forces, so we have whether we are talking about hydrogen bond, okay, PD or ID. Okay, so C1, okay, C1 is a cyclopentane. Okay, so we can see cyclopentane over here. Okay, first of all, okay, the cyclopentane, in order to have hydrogen bonding, you must have bonding between hydrogen and NOF. Okay, there is no O, there is no N, there is no F. Okay, so therefore we can eliminate hydrogen bonding. So we are talking about maybe PD or ID. Now, so let's see whether there is a presence of PD or not. Okay, should not be any presence of PD because carbon and hydrogen, okay, the electronegativity is similar. Okay, so there is we cannot say cyclopentane is we can say that cyclopentane is a non-polar molecule. Now, if it is non-polar molecule, okay, so generally they only have ID. Yeah. So generally ID, so we can say that the boiling point and melting point, okay, is actually low. Okay, so C1 has low boiling point and low melting point. Why? So we just have to mention about the ID. Yeah. So here, okay, let's look at the marking key. Okay, so even here they say C1, okay, C1 has, okay, boiling point and melting point are low because weak van der Waals forces. Okay, and then we tell which one. So they even mention is instantaneous dipole, induced dipole. That's it. So C1 has low melting point and low boiling point because it has weak van der Waals forces. The van der Waals forces are only ID. Okay, you must mention instantaneous dipole, induced dipole. Or if you don't want to mention, don't want to write the full version, you can say London forces, or you can say dispersion forces. Okay, you can actually choose one. Okay, don't choose everything. Okay, so only London forces, dispersion forces, or ID, which is present. Yeah. Now, the next question. Okay, draw the structure of cis isomer of C2. Cis isomer of C2. So here they have given like this. Okay, so you want cis isomer. So you can either use skeletal formula, display formula, up to you. Okay, but if you look over here, carbon, okay, carbon is here, double bond, this carbon. So this one C, so this one is C3H7, and then there is H, and then here is CH3, and then H. So I want a cis isomer. Okay, so the cis isomer is going to be, currently this is trans, so cis is going to be, you can just draw C double bond C, you can put the CH3 here, and then you can put the C3H7 here, and then put H. Okay, you can leave it like this, it's okay. So even in the marking key, they said, yeah, you can actually leave the answer in skeletal formula, or you can write, okay, like this. So it's fine. Okay, now C2 forms a polymer when heated gently. So C2, okay, so anything that has double bond, so they do addition polymerization. So identify, so addition polymerization. Draw one repeat unit. Okay, when they say one repeat unit, there is no double bond. Yeah, so what we normally do, okay, so we are talking about C2, so we must actually use this one. Okay, so the answer is this. Okay, This is the answer. Okay, so I will bring this one down. So normally what we do first, okay, we actually put the hydrogen like this. Then we erase this one, CH3, we put it like this. We erase this one, C3H7, we put it like this. Hydrogen, we put it like this. And then now you delete, you erase the single bond, one of the bond over here, open the arm. Open the arm, open the arm. Okay, so this is one repeating unit. Okay, done. Okay, so we will look into question number 5. Okay, so you have lactones are cyclic ester. Okay, so under certain condition, they are going to form from molecules, okay, from alcohol, and those contain alcohol and carboxylic acid functional group. So this is an example, okay, of this formation of lactone. So the normally, yeah, so if you have alcohol and carboxylic acid, okay, the hydrogen will come from the alcohol, OH will come from carboxylic acid, so water will be released, and you are going to have this lactone, which is going to be ester group. Yeah. So figure 5.1 shows the synthesis of lactone from a compound M. So this is the compound M. It contains double bond, and when we use hot concentrated acidified KMnO4, what happens? The double bond is going to be broken. Okay, so you will have oxidation of the double bond, and we are going to get N. Okay, so let's solve the question. M reacts with hot concentrated acidified KMnO4, okay, to form C6H10O3. Okay, so it means that it's going to be 3 oxygen over there. Okay, in reaction 1. Okay, so what will happen? Okay, let's look at it. Okay, so if you have carbon over here, okay, this is going to be 1R group, and this is hydrogen, and then this is going to be another carbon. This is 1R group and another R group. So what will happen when the double bond is broken? You are going to have, okay, this side on the right hand side, oxygen will come, and then left with the R and left with the R. So this is going to be a ketone. And then if you continue, okay, this one, this side, okay, you have carbon, you have double bond O, okay, there is 1R group, this is R group, and then H, okay, this one will continue to change into carboxylic acid. So we will have this kind of group. So in the end, the bond is broken. Okay, so we can have total of 1, 2, 3, 4, 5, okay, and then 6. Okay, 6 carbon. So we can actually just draw like this: 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 6 carbon, and then here at the first carbon there is carboxylic acid, so we can actually draw like this: OH, carboxylic acid, and then at carbon number 2 on the right, you can actually draw the ketone, okay, the ketone group. Okay, so double bond O. So this is going to be the structure of N, so we can actually just bring it over here. Okay, begin. Okay, this is the structure of N. Okay, so this one we can always check with the marking key. Okay, we can see the 1, 2, 3, 4, 5, 6. Okay, so you have 6 carbon. Okay, here also we have 6 carbon. 1, 2, 3, 4, 5, 6. Yeah, everything is correct. Now, next is going to be N is reduced by NaBH4. It's a mild reducing agent. Okay. So to 5-hydroxyhexanoic acid in reaction number 2. So in this case, what we can see is the carboxylic acid group, okay, it remains, okay, but the ketone part, okay, the ketone part over here, they are going to change into OH. Okay, so this one is reduction of ketone. Okay, reduction of ketone will give you secondary alcohol. Okay, so basically we are going to have the secondary alcohol over there being formed. So we need to construct an equation. So what happens generally, okay, if I copy this structure again and I put it here, generally what happens, okay, the double bond, okay, the double bond O will be broken, and we are going to have, okay, the hydrogen coming in here and hydrogen going in there, so it will form a secondary alcohol. So in this case we are talking about 2 hydrogen, okay, being added over here. So we can just simply put, okay, we can just count over here, okay, so 1 carbon, 1 2 3 4, okay, actually no need to count, they have already given, yeah. So N is going to be C6 H10 and O3. So that's going to be N. So N is going to be reduced, okay, so hydrogen, and they are going to have 2 hydrogen going in, okay, so you have C6 H12O3, okay, the 2 hydrogen went in, so we need to put 2 there, that's it, okay. Now reaction 2 is a nucleophilic addition, yeah, so anything that has this carbonyl group, okay, aldehyde and ketone, they call it as nucleophilic addition reaction. Now suggest why reaction 2 creates a mixture of 2 organic compounds. Okay, so when we have, okay, the product, okay, so what happens, this part, okay, we know that previously we had the double bond O here, okay. So now what happened, okay, previously when it was like this, okay, this molecule was planar, okay. So this planar molecule, okay, can be attacked by the nucleophile at 2 different directions, okay. If it is planar, let's say for example, okay, you have 3 bonding pair, okay, it's a planar molecule, okay. So if I attack, I can attack from the top, I can attack from the bottom, okay. So that is going to be the explanation. So reaction 2, okay, so you can say that the molecule, okay, 5-hydroxy hexanoic acid is planar and can be attacked by nucleophiles from 2 directions to create or to produce, okay, I think better to say to produce okay, C6H12O3, which has a chiral center at carbon number 2, okay, if it is carboxylic acid, okay, this one 1 2 3 4 5 at position carbon 5, carbon number 5, which can form optical isomerism. Okay, that will be the answer. Now next, draw lactone P, the product of reaction 3. So the product of reaction 3, so we have, okay, we have this this molecule, so I can copy this molecule, and then we are going to try to form the lactone. Okay, so what happens, okay, we are going to have the OH, okay, from the carboxylic acid, the H from the carboxylic acid will give you water. Okay, so we are going to have, okay, carbon. Okay, so this carbon, so I just put this carbon has double bond O, and then there is one more carbon. Okay, so 1 2 3 4 5. Okay, after that, okay, this hydrogen will come over here, they will close, okay, the cycle, they will form a cycle. So it's going to be 5 carbon. So let's actually put, okay, 5 carbon. So it means 1 2 3. So you see 1 2 3 4 5. Okay, so 5 carbon. And then at carbon number 5, okay, there is CH3. So carbon number 5, there is CH3. Okay, so before that, I think I forgot. Okay, there's O at carbon number 5. Okay, so carbon number 5 will have O. So this one, I think need to draw again. So like this, like this, like this, O, and then join. So carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay, CH3 will be here. Okay, so this is going to be the structure of lactone. Now, student monitors the progress of 2 using infrared spectroscopy. Use the table 5.1, suggest why it's difficult to distinguish between N and 5-hydroxyhexanoic acid. Now, hydroxyhexanoic acid has OH, and then it has COOH. N, on the other hand, okay, N is going to be, this is the structure of N. There is also C double bond O, okay, and then carboxylic acid. Okay, so C double bond O and then COOH. First thing that we notice is, okay, if you have carbon COOH, okay, this is going to be OH for carboxyl. Okay, this is going to be the values, and this is going to be the values. Okay, but we see that both of them, okay, have this COOH. Okay, and then we need to check also there is OH. Okay, the OH is happening here, okay, at this part. And then for C double bond O, okay, C double bond O, we can see that, okay, they also, okay, for ketone, okay, we see it is going to overlap. Okay, the ketone is going to overlap with this. Okay, so first thing, okay, we know that there is an overlap for C double bond O for carbonyl and carboxyl. Okay, that's one of the problem. Okay, there's an overlap. Okay, and then, okay, we know that, okay, both of them also have COOH, okay, together. Okay, that will actually make it more difficult. Okay, because one is there is an overlap, another one there is COOH. Okay, and then even though one of it has OH, okay, because of there is carboxylic acid over there, it's going to be difficult, okay, to just find there is going to be hydroxy. There is also overlap for that also. Okay, so and there is similar environment for OH and, okay, similar environment, so for OH and carboxyl group. Hydroxyl, N carboxyl group. Okay, that's going to be difficult, okay, for us to identify. Now, next, okay, unknown lactone Q is analyzed using mass spectrometry. So here they have given you the peak for M plus, okay, and then M plus 1. So what we can do, okay, we need to deduce the structure of Q. What we can do from this data is to find the number of carbon that is involved in this molecule. So how to find? We just use the formula, okay, which is going to be 100 divided by 1.1 times the abundance, okay, abundance of M plus 1 divided by abundance of M plus. So 100 times abundance of M plus 1 is 3.15. 1.1 times, okay, abundance of M plus is going to be 95.5. So if we calculate this, so let's calculate this. 100 times 3.15 divided by 1.1. Hold on.
Oh.
Video. Okay, 1.1 times 95.5. Close the bracket. 2.999. Okay, you'll get 2.999, which is 3. So it means we have the number of carbon is going to be 3. So it's lactone. Yeah, lactone is going to be a cyclic compound, okay, which has C double bond O and O, yeah, cyclic compound. Okay, so what we can do is, okay, 3 carbon, so 3 and then plus oxygen, so maybe it will be like this. It's supposed to be like this, 3 carbon, okay, 3 carbon, and then there is oxygen, okay, we can draw like this, and then there is going to be oxygen over here, okay, that's lactone. So we can draw like this, O, okay, no need to show the carbon, okay, skeletal formula. So every single time when you have, let's say you're not sure structure, you refer to the question. If the question is in skeletal formula, then we answer in skeletal formula. Now, so show your working. Yeah, this is my working. Okay, you can actually bring it down here. Okay, this is my working. Okay, we deduce this is the structure. Okay, and that's it. Okay, see you guys.